Now that we've written down all of Maxwell's equations, we can look at the properties of electromagnetic waves. So here are Maxwell's equations. Gauss's law for the divergence of E, Faraday's law for the curl of E, Gauss's law for the divergence of B, and the Ampere-Maxwell law for the curl of B, including Maxwell's postulated displacement current. Rho is charge density, J is current density, so these are related to particles carrying charge. But we're going to be interested in electromagnetic waves. The solution of these equations where rho and J are zero. So in other words, fields in empty space. Fields and there are no charges. Now, we'll find the solution in terms of harmonic waves. So before we go on, let's review what is meant by harmonic waves. Consider this function. U of x and t is some constant u0 cosine kx minus omega t. It's a sinusoidal function in both position and time. So, in other words, it oscillates in x and it oscillates in t. If I plot u of x and t at a particular value of t, I get a cosine dependence on x. So I get a oscillating function of x. That's one particular value of t. Now, if I plotted again u of x at a different value of t, I would again get a cosine oscillation of x, but it would be shifted in position. So here's a figure from the book, a sinusoidal traveling wave. The blue curve is this function as a function of x for some value of t. So the blue curve is u of x and t1. T1 could be approximately pi. The cosine would be minus 1 if, I should say pi over omega. Pi over omega. Then the red curve is u of x and t2, where t2 is a later value of time, let's say 2 pi divided by omega. So, you see at time t1, you had this wave, this blue curve. Oh, and I should say this goes on for larger value of x and smaller values of x. It's only been plotted for a limited range of x, but you should imagine this thing extending out to large values of x and large values of negative x. All right, so at some time I have this blue curve. At a later time, the curve has moved over. And I have this red curve. It'll have the same shape, it'll just be located at a different place. So, as a function of time, the wave is traveling along in the positive x direction. So that's called the propagation direction. And you can imagine making a moving picture of this wave where it would be continually moving along, maintaining its shape, but just moving as a whole in the direction of x. All right, so that's the kind of harmonic wave which we're going to find for the electric and magnetic fields. Now, there are a number of parameters which define a wave. And I have this functional form, cosine kx minus omega t, and that depends on three parameters actually, u0, k, and omega. I should be able to relate all other wave parameters to these three. All right, so this is u as a function of x at a particular value of t, or actually two particular values of t. t1 is the blue curve, t2 is a time t later, where the curve has moved over from the blue position to the red position. So during that time, t, the wave has moved by a distance v times t, where v is called the wave velocity. Well, okay, so how is the wave velocity determined by these three parameters in the function, u0, k, and omega? Well, let's look at a number of different parameters. First of all, there's the amplitude. The wave, you see, as a function of x, the wave varies between plus u1 and minus u1. So here's u0. So here's u0, and here's minus u0. And if I look at the wave at a particular time, and I look at its range of values as a function of position, it varies between plus u0 and minus u0. That's called the amplitude, or the amplitude of oscillation. The cosine oscillates between minus 1 and 1, so u oscillates between minus u0 and u0. So u0 is the amplitude. Now that's the amplitude for variations of x with fixed t, but it's also the amplitude for variations with respect to time at a fixed x. If I chose one value of x and I just watched the value of u as the wave passes over me, if I'm standing right here and the wave is passing me by, I'll see as a function of time a variation between minus u0 and plus u0, and back to minus u0 and up to plus u0. In other words, it oscillates in time with the same amplitude, u0. All right, now what's this parameter k? K is called the wave number. It's not a pure number. It has units 1 over length. So k would have units of 1 over meters. So that k times x would be dimensionless, because I can only take the cosine of a dimensionless number. Or I could say kx could be radians, and then k could be radians per meter. But usually we just say k is some number of inverse meters. Now what about the wavelength? The wavelength is from, let's say, from one peak to the next peak at a fixed time. So that distance is the wavelength. You sort of have the crests and the troughs. The distance from one crest to the next crest is one wavelength. That's the same as the distance from one trough to the next trough. That's called lambda. Now, you know the behavior of the cosine is, if I change the argument of the cosine by 2 pi, I'm back at the same value of the cosine. In other words, if I add 2 pi to this value, I'll be back to the same place on the cosine function. So if I change kx by 2 pi, I go from the crest to the next crest, or the trough to the next trough. So k times the wavelength is 2 pi, or the wavelength is 2 pi divided by k. So this parameter k, which appears in the functional form, and which I call wave number, it's really related to the wavelength. K is 2 pi over the wavelength, or the wavelength is 2 pi over k. Now what about omega? Omega is called the angular frequency. So that's just its name. It's angular frequency. If I pick a particular value of x, let's say one particular value of x, and I sit right here, I see a sinusoidal variation which goes like sine omega t. Now, again, if omega t changes by 2 pi, I go back to the same point on the wave. So if I'm at a maximum and I wait until omega t has changed by 2 pi, I'll be back at the maximum, standing at the same point in x. So therefore, the period is the time when omega t, or the change in time, where omega t changes by 2 pi. So t changes by 2 pi divided by omega. So the period of oscillation is 2 pi over omega. Just like the length of oscillation, we call it the wavelength, is 2 pi over k, the period of oscillation is 2 pi over omega. Now what about the frequency? Well, the frequency is 1 over the period. So suppose the period is 1/60th of a second. Then the frequency is 1 over 1/60th of a second. It's 60 cycles per second, or 60 hertz. Now I can also write that in terms of omega. 1 over t is omega over 2 pi. So the frequency is omega over 2 pi, or another way to say it is omega, the angular frequency, is 2 pi times the frequency. So frequency is 1 over time. 2 pi radians per second gives me the angular frequency, radians per second. All right, so you have to often be careful not to confuse angular frequency and frequency. Frequency means 1 over the period. Angular frequency is the frequency times 2 pi to convert it into radians per one cycle is 2 pi radians. Now I said this wave is moving along bodily, retaining its shape with some velocity. Well, what's the velocity? I should be able to determine it in terms of these parameters omega and k. Well, if I wait one period, the wave will move by 1 wavelength. So the velocity is 1 wavelength divided by 1 period. It's lambda divided by t. Or I could say it's omega divided by k, because lambda is 2 pi over k, t is 2 pi over omega. The 2 pi's cancel, I get omega over k. So in terms of these parameters that I use in writing down the harmonic wave, the velocity is omega over k. But in terms of this geometrical picture, it's the wavelength times the time. Divided by the period, rather. Let's consider an example. Suppose k is 2 inverse meters. And suppose omega is 2 radians per second. Then what's the wavelength? Well, the wavelength is 2 pi over k. 2's cancel, it's pi meters. It's 3.14 meters. What's the period? Well, the period's 2 pi over omega. So it's 2 pi over 2. It's pi. It's 2 pi radians over 2 radians per second. So it's pi seconds. It's 3.14 seconds. And what's the velocity? If the wave number is 2 and the angular frequency is 2, what's the velocity? Well, remember, velocity is omega over k. So it's 1 meters per second. These parameter values, wavelength of 3 meters, velocity of 1 meter per second, that could describe, for example, a water wave near an ocean beach. You know, the distance between waves, that's the wavelength, from one crest to the next crest, would be a few meters, might be 3 meters. And how fast do waves travel near an ocean beach? Well, about 1 meter per second, I suppose. So these parameter values could describe a water wave near an ocean beach. What would U be in that case? You know, what's waving? What's oscillating? Well, it's the depth of the water. Or I could say it's the height of the water surface above some equilibrium depth as a function of position and time. So you could be taken as, let's say at this beach the water is normally, I don't know, 2 meters deep. Well, now I have waves on the surface of that 2 meter equilibrium position, which would have some amplitude of oscillation between U0 and minus U0. So you would see the waves being 2 times U0 from crest to trough, where, again, that's the displacement of the water from the equilibrium depth. You know, let's say the equilibrium depth is, I don't know, 2 meters or something. But the water surface is oscillating in position. And the whole wave is moving to the right, let's say, so it's, for any position, it's oscillating in time. So that's a water wave at a beach. For surfing, you would want U0 to be about a meter. So you put your surfboard here, and you'll be carried along on that wave at a speed of about 1 meter per second. So we've seen how the mathematics can be used to describe a wave. For example, a water wave, or any kind of wave. Same thing could describe a sound wave. Well, we want to apply that now to electromagnetic waves. So now, what's undulating? You know, what's oscillating? It's the electric and magnetic fields. So we'll have an electric field which depends on position and time, and we'll have a magnetic field which depends on position and time. And they have to go together and satisfy Maxwell's equations. Now, let's consider a wave that's just traveling in the z direction. So let's say its electric field depends on, oops, this is wrong. It depends on z. And its magnetic field depends on z. The wave propagates along the z-axis. Well, here's a typical electromagnetic wave. It'll be oscillating in the x direction. The electric field will be oscillating in the x direction. The magnetic field will be oscillating in the y direction. And that's typical of electromagnetic waves. If the electric field oscillates in one direction, the magnetic field oscillates in a perpendicular direction. They both oscillate in the directions perpendicular to the direction of propagation. So it's what's called a transverse wave. The oscillations are perpendicular to the direction of motion. This would be called polarized in the x direction because the electric field is oscillating in the x direction. It's pointing in the positive x direction, then the negative x direction, then the positive x direction. If I sat right on one point, as this wave went by me, I would see the electric field oscillating between positive x and negative x. Well, as a vector. In other words, it would be oscillating between the I hat direction and the minus I hat direction. And meanwhile, the magnetic field would be oscillating between the plus j hat direction and the minus j hat direction. And in the meantime, the whole wave moves bodily, both the electric field and the magnetic field together, in the z direction. So the fields depend on z. I've assumed that it's sort of an infinite wave, so I've assumed that the wave front is a plane, and it's the same for all the x and y values. See, this plane has a particular value of z. It happens to be z equals 0. And I'm saying the electric field doesn't depend on the y and z point on this plane. So here's a particular point of the plane, the origin. But if I looked up here at this point, I would see the same kind of, oscillations of the electric field in the x direction and the magnetic field in the y direction, just propagating along that position in x and y. So it's kind of plane. So it's called a plane wave. It's a plane wave because the wave fronts, let's say the positions where the wave is at its crest, are planes parallel to the xy plane. So that's a typical kind of electromagnetic wave. Polarized in the x direction, propagating in the z direction. And here would be the electric fields for that picture. The electric field is I hat E0. So E0 is the amplitude of oscillation of the electric field times sine kz minus omega t. I call it sine because if I set t equals 0, this would be a sine function. It starts at z equals 0. Sorry, if I set t equals 0, this is a sine of kz. And the magnetic field is the same sinusoidal function, sine kz minus omega t. But it's in a perpendicular direction, j hat. And it has an amplitude B0. Now the amplitude of the electric field, the amplitude of the magnetic field can't really be the same. Well, no, of course they can't be the same because they have different units. So E0 will be some number of volts per meter. And B0 will be some number of Teslas. Now what we're going to find when we solve Maxwell's equations is that E0 and B0 are related. They can't be equal because they don't have the same units. But they're very closely related. They're proportional. And we'll come to that in a few minutes. So this is the picture. It's taken from the textbook. And you can find a picture like this in any textbook on electricity and magnetism. Or if you looked up on Google, picture of an electromagnetic wave, it'll show you this. The electric field oscillating. This is a harmonic oscillation. The magnetic field oscillating. The nodes are at the same places. The crests and the troughs are at the same positions. The wavelength is from one, well, let's say one trough to the next trough. So the electric wavelength is the same as the magnetic wavelength. It's the same wave number for both the electric field oscillations and the magnetic field oscillations. And furthermore, they have the same frequencies. They have the same angular frequencies and same frequencies. So we're going to see that these satisfy Maxwell's equations, but it'll only work if they have the same wave number and frequency. So here are my harmonic waves, sinusoidally oscillating in position and time. E is polarized in the X direction, B oscillates in the Y direction, and again, I have a mistake here. It's propagating in the Z direction. So the position dependence is Z. Now I want to show that these solve Maxwell's equations. Maxwell's equations in empty space. So Maxwell's equations with no charges, no currents, just vacuum. So I'll take Maxwell's equations and I'll set rho equals 0. And I'll set J equals 0. And now I'll calculate the divergence and curl of E and B. So let's start with Gauss's law. Gauss's law with rho equals 0. I have the divergence of E. That's dEx dx, dEy dy, dEz dz. But there's only an EX. E only has an X component. So it'll just be dE dx. Well, that'll be E0 times d dx of sine kz minus omega t. Well, this doesn't depend on x. This is a partial derivative. It means differentiate with respect to x, holding y and z constant. Well, this is a constant as far as x is concerned. And the derivative of a constant is 0. So del dot E is 0. Gauss's law is satisfied. The divergence is 0. It's obeyed because the electric field is perpendicular to the direction of propagation. You know, it's propagating in the z direction, but it's oscillating in the x direction. So electromagnetic waves are transverse waves. And that's why Gauss's law is satisfied. Because when I take a derivative with respect to x, it hits a function which doesn't depend on x. And if E is only pointing in the x direction, then this divergence only involves the x derivative. Okay, so Gauss's law is satisfied, with no charges, of course. Now, as long as we're doing Gauss's law for electricity, we might as well look at Gauss's law for magnetism. The divergence of B, that has to always be 0, because there are no magnetic charges. Well, again, B has only a y component. So this is dBx dx plus dBy dz plus dBx dx plus dBy dy plus dBz dz. Well, the only thing that's not 0 is By. So del dot B is dB dy. So it's d dy of B naught sine kz minus omega t. So d dy sine kz minus omega t. Well, that's 0 for the same reason. This doesn't depend on y. So it works. We satisfy Gauss's law for magnetism because the magnetic field is also transverse. Next we have Faraday's law. Faraday's law is an equation for the curl of E. So let's calculate the curl of E. Remember the curl? The curl is well, it's that determinant. You know? What's the curl of E if E only has an x component? Well, it'll involve terms that go like dE dy, dEx dy, and dEx dz. Remember, the curl is derivatives, partial derivatives, in opposite directions from the component of E. Well, E only has an x direction. So I could have terms with dEx dy. But I already saw E doesn't depend on Y. It only depends on Z. So the term will be dEx dZ. And that part of the curl is in the J direction. You know, you have to write down the curl as a determinant in Cartesian coordinates with ijk, dx, dy, dz, and ex, ey, ez. Well, the only term which is not zero is this term and this term, because that's the ddz. So these two terms. So the only one that'll survive in this determinant will be j hat 0 minus, well, minus j hat times minus dz All right, so we calculate dEx dz. All right, well, here's Ex. It's E naught, the derivative with respect to z. Derivative of the sine is a cosine times k by the chain rule. So it'll be k cosine kz minus omega t. J hat E0 k cosine omega t. Now Faraday's law says curl of E is minus dB dt. So what's minus dB dt? Well, I have minus, now B is in the j hat direction. So it'll just be j hat, B0 is a constant. I just have to differentiate sine with respect to t. Well, that'll be cosine times minus omega by the chain rule. So I have minus omega cosine kz minus omega t. Those should be equal. That's Faraday's law. Well, they have the same z dependence. They have the same t dependence, so that's looking pretty good. They have the same direction. They're equal if E naught k is the same as B naught omega. So Faraday's law is obeyed, provided you have this relation between E naught, B naught, k, and omega. K E naught has to be the same as omega B naught. So we'll remember that equation. That's equation 1. It's a relation between the size of the fields, E naught and B naught, and the wave parameters, k and omega. So that's working. And the final equation is the Maxwell Ampere Law with J equals 0. Since J is equal to 0, it's not really the Ampere Law anymore, it's just the Maxwell Law. It's for the equation for the curl of B. B is mu naught J, but J is 0, plus it's mu naught times the displacement current. So let's calculate the curl of B. Well, once again, the only contribution from the gradient is the ddz part. B only has a y component, so I'm going to have ddz by, that'll be in the I direction. Or actually be in the minus I direction if you look carefully at this determinant. So it'll be minus I hat dby dz. A little tricky to get the sign right, but you have to look at this determinant. Now, dby dz is easy to calculate. I just differentiate this with respect to z. I get b naught k cosine kz minus omega t. So here's the b naught k cosine kz minus omega t. And that should be equal to mu naught times the displacement current, epsilon naught dE dt. So let's calculate mu epsilon dE dt. So I have mu epsilon. Now E is in the I direction. That doesn't change in time, so I'll still have I hat, E0 is a constant. I'll just have d dt of sine kz minus omega t. Derivative of sine is a cosine. I have to differentiate the argument of the sine. That'll be minus omega by the chain rule. So I got minus omega cosine kz minus omega t. Now are these equal? Well, they have the same z and t dependence. They have the same direction, I hat. They're equal if they have the same sign. This one's negative, this one's negative. They're equal if this coefficient, B naught K, is the same as this coefficient, mu epsilon omega E naught. So that Maxwell Ampere Law is satisfied provided KB0 is mu naught epsilon naught omega E0. That's another relationship similar to what I had before, relating the size of the amplitudes of oscillation, the sizes of the electric and magnetic oscillations, relating the wave parameters K and omega, and involving this universal constant. Remember, mu naught is the constant which determines the strength of magnetism. And epsilon naught is the constant that determines the strength of electric forces, strength of electricity. Well, that's going to have to come into this electromagnetic field analysis. It comes in as the product mu naught epsilon naught. This is all for waves in empty space. If I had electric and magnetic waves traveling through a material, like let's say glass or water, a transparent material, light, well, we're going to see that electromagnetic waves are a form of light, but let's just say that for a transparent material, a material that the waves will travel through, these two constants, the constants of magnetism and electricity, would be different. They would depend on properties of the material. These are the values of those parameters for empty space. Now, if we put in the magnetic properties of the material, the electric properties of the material, then we're going into optics. And that's not part of Physics 234. But all you have to do in order to study optics is replace the magnetic and electric constants for vacuum by the values for materials, transparent materials like glass or light or water. All right, so Maxwell discovered that his equations are obeyed for harmonic traveling waves. But there are two conditions. So the waves are related by these two relations. And so the next thing we have to do is we have to see what they imply. We'll learn some properties of electromagnetic waves from those two equations that were required by Maxwell's theory. And these properties of electromagnetic waves you're going to need for the Lon-Kappa problems. So one of the equations was K E0 has to be omega B0, or B over E is K over omega. And the other equation was K B naught is mu naught epsilon naught omega E naught, or B naught over E naught is mu epsilon omega over K. So here I have two equations. It's those same two equations I derived a minute ago. The conditions for satisfying Maxwell's equations. Now, one property I can get immediately is the speed of electromagnetic waves. Again, I'm talking about electromagnetic waves in empty space. Go back to where we talked about harmonic waves. Remember, the wave speed was omega over K. That's just a general property for all harmonic waves, harmonic traveling waves. So the speed is omega over K. Look at this equation. I can determine omega over K. Multiply both sides of the equation by omega, divide by K, divide both sides of the equation by mu naught epsilon naught. So you get omega squared over K squared is 1 over mu naught epsilon naught. Take the square root of both sides of the equation. Omega over k is 1 over the square root of mu naught epsilon naught. That's V. So these waves have something very remarkable. They all have the same speed. This is an empty space. Waves in a material like glass or water, that's a little different because mu and epsilon can depend on k and omega. But never mind, that's optics. For waves in vacuum, they all travel with the same speed. There's a universal speed of light. And we call that c. So in physics, the letter c always stands for the speed of light in vacuum. It's universal. It doesn't depend on omega. It doesn't depend on k. It only depends on these universal constants, mu naught and epsilon naught. It's just a universal constant of nature. All electromagnetic waves travel at the same speed. So if you have a wave with a short wavelength, it'll travel at a certain speed. That could be an X-ray. Or if you have a wave with a long wavelength, it'll travel with the same speed. That could be a radio wave. The speed of electromagnetic waves is a universal. By the way, that fact is the beginnings of Einstein's theory of relativity. All right, now what's the value of this number? Well, Maxwell knew it because from electric and magnetic measurements, he knew the value of mu zero. Remember, that has to do with the strength of magnetic forces. Well, those had been measured, people like Ampere. Mu naught is 12.6 times 10 to the minus 7 in the standard units that we use today, SI units. The same way with epsilon naught. That was measured by Coulomb because it has to do with the strength of the force between charges. It's 8.9 times 10 to the minus 12 in SI units. So Maxwell had this result, and he plugged in these numbers, and he calculated 1 over the square root, and he found 3 times 10 to the 8 meters per second. And he knew that's the speed of light. That's the speed of light in air. You know, optics had been studied for a long time. Optics had been studied since the time of, well, since the time of Newton, really. Optics had been studied for more than 100 years, and the speed of light had been determined. The speed of light was determined long before Newton. Actually, the speed of light was determined a little bit before Newton. Galileo tried to measure the speed of light, but he failed because it was too fast. His method for determining the speed, he couldn't measure such a fast speed. But there was an astronomer who followed Galileo's discovery of the moons of Jupiter and used delay times in observing the moons of Jupiter to determine the speed of light. So Maxwell said, look, I have this theory. There are waves. They travel at 3 times 10 to the 8 meters per second. That's the speed of light. So Maxwell concluded that light is an electromagnetic wave. It was already suspected before Maxwell, although not agreed by everybody, but it was pretty well suspected by the time of Maxwell that light consists of waves because people had observed interference of light waves. Not everyone accepted the theory that light is waves. Some people thought light is made of particles. That's what Newton thought, but this was much after Newton. So the fact that light was made of waves is not too surprising. The fact that it was electromagnetic was the big surprise. So Maxwell's field theory, published over 100 years ago, is, even today, the unified theory of electricity, magnetism, and optics. Well, we're almost done, but remember there was another relationship that was required for the wave solutions to obey Maxwell's equations. And that leads to a relation between the amplitudes of oscillation of the electric and magnetic fields in an electromagnetic wave. B naught over E naught is K over omega. And K over omega is 1 over the speed of light. So the size of the electric field oscillations is equal to the speed of light times the size of the magnetic field oscillations. So you see, E naught and B naught aren't equal. Well, they can't be equal because they have different units. I mean, E naught is volts per meter. B naught is Tesla. The difference between volts per meter and Tesla is seconds per meter. So if I multiply Tesla by meters per second times Tesla is volts per meter. And the constant I should multiply it by is what else? What else could it be? There's nothing else with the right units. It's the speed of light. There will be a lot of Lon Kappa problems where you have to know this. Now, the electric and magnetic amplitudes are not equal, but the energies are equal. So, here is something taken from the textbook again. The energy in an electromagnetic wave. I know the equations for field energy densities from the studies of capacitors. The energy density of an electric field is 1/2 epsilon naught E squared. So let's put in E. E naught cosine kx minus omega t. I never fixed that, did I? Kz minus omega t. And the field energy of the magnetic field is 1 over 2 mu naught B squared. We learned that from inductors. Remember, the energy of an inductor was 1/2 Li squared. Well, I is related to B, so you can rewrite this in terms of B, and when all is said and done, the magnetic field energy is B squared. The electric field energy is E squared, the magnetic field energy is B squared. Well, times epsilon naught over 2 for the electric energy, times 1 over 2 mu 0 for the magnetic energy. So let's put in B. B naught cosine kz minus omega t squared divided by 2 mu naught. They both oscillate in time, but they don't oscillate between a positive and a negative value because energy is always positive. They oscillate between 0, cosine squared oscillates between 0 and 1. Cosine oscillates between minus 1 and 1. Cosine squared is between 0 and 1. So the energy density in the electric field oscillates between 0 and 1/2 epsilon naught E0 squared. And the magnetic field oscillates between 0 and B naught squared over 2 mu 0. Now, these coefficients are equal. Let's look at epsilon naught E naught squared and divide it by B naught squared over mu naught. So I have E0 over B0 squared. Well, that'll be C squared. So there's the C squared. And I have, multiply numerator and denominator by mu naught, I'll have mu naught epsilon naught in the numerator, mu naught epsilon C squared. But C is 1 over the square root of mu epsilon. So this is 1. So the electric field is always equal to the magnetic field for electromagnetic fields in empty space. Now, because these are oscillating functions, we usually calculate the average over time. The average over time, well, cosine squared, as a function of time, varies between 0 and 1, so the average is a half. So for the electric field energy, it's 1/4 epsilon naught E0 squared. For the magnetic field energy, it's 1/4 mu naught B0 squared. Then these two are equal because of the relationship between E naught and B naught, and the relation between epsilon naught mu naught and the speed of light. Now, of course, the energy density, the average energy density in the electromagnetic wave will be the sum of the two, the electric energy plus the magnetic energy. Or I could just say it's 2 times the electric energy, because it just turns out that the magnetic energy is the same as I could say it's 2 times the electric energy, or I could say it's 2 times the magnetic energy. But I guess physically it's really the sum of the two. Now those are energy densities. The power in light is usually expressed in terms of light intensity. So here's a subject. I don't really have time for it in the screencast, but you'll need it for the homework. Light intensity. What's the power in a light wave or any kind of electromagnetic wave? It's determined by what's called the pointing vector. And so you'll have to read the section in Fisher about the pointing vector. The pointing vector is the power per unit area. It turns out that the power per unit area is just the speed of light times the energy density. So to obtain this result, you have to go through the derivation of power, which is given by the pointing vector. The pointing vector is E cross B divided by mu 0. Divided by mu 0. That's called the pointing vector. It's a vector. Kind of a complicated thing because it involves a cross product. It points in the direction of propagation. E points in the x direction, B points in the y direction, E cross B points in the z direction. So it points, the wave travels in the z direction and it transports energy in the z direction. How fast does it, how much energy does it transport per unit time? Well, that's called the pointing vector. And you'll have to read about this in the book, but the final result is that that's equal to C times the energy density. We can check the units. C is meters per second. Energy density is joules per cubic meter. So 1 power of meter cancels. Joules per second is watts, so it's watts per meter squared. So that's the measure of light intensity, power per unit area. And again, there'll be some law and kappa problems where you have to know that. So you'll have to dig that out of the book to solve the law and kappa problems. Well, there's nothing in Maxwell's theory that limits the wavelength. Any wavelength is possible. It's just all values of k are possible. K is 2 pi over the wavelength. All wavelengths are possible. All frequencies are possible, although the frequency is related to the wavelength. The frequency times the wavelength is equal to the speed, and the speed is a universal constant. So here's a figure from the book again. Here's a range of wavelengths from 1 meter to 10 to the minus 14 meters. And there's an equivalent range of frequencies from 3 times 10 to the 8th cycles per second 3 times 10 to the 8 oscillations per second, or 3 times 10 to the 8 hertz, to, I guess this would be 3 times 10 to the 24th cycles per second. So here's very high frequencies. High frequencies have short wavelengths. Here are sort of low frequencies. Well, not all that low. 3 times 10 to the 8th is not a small number, but it's kind of a long wave. Its wavelength is a meter. Maxwell predicted, through his theory, all of these kinds of electromagnetic waves. In his day, what was known was visible light. That's all. Infrared light and ultraviolet light were discovered later, but they were already described by Maxwell's theory. Ultraviolet has shorter wavelengths, higher frequencies than visible. Visible is this range from 700 nanometers down to 400 nanometers. Anything with a lower wavelength is not visible, at least not to humans. Anything with a higher wavelength is not visible, at least not to humans. This is what we can see. Unless you're colorblind, you can actually distinguish between different waves in this band. They have slightly different wavelengths. They have slightly different frequencies. In the quantum theory, they have slightly different photon energies. That's why you can distinguish, because you have cells in the back of your eye which react differently to different energies, photon energies. Well, anyway, ultraviolet and infrared waves predicted by Maxwell, discovered later. X-rays. X-rays were called X-rays because nobody knew what they were. Well, eventually they figured out they're electromagnetic waves, described just as well as visible light by Maxwell's theory. Gamma rays are like super duper X-rays, very high energy X-rays, and cosmic rays. So gamma rays come out of nuclear reactions. Cosmic rays come out of processes that occur in the universe, outside of the Earth. For the long wavelengths, well, there's infrared. You've sat in front of a fire and felt the heat. That's infrared waves. That heat is infrared electromagnetic waves impinging on your skin, and it feels hot. You go a little higher, you come to the microwaves, which we use every day to cook our food. And then radio waves for communication, waves for communication like television, radio, Wi-Fi, your cell phone. Every one of these different kinds of electromagnetic waves has important applications in everyday life. They were not known at the time of Maxwell, but they were predicted by his theory. Now, there's one other topic in the chapter on electromagnetic waves. It's the topic of antennas. It's a little too involved to actually derive the equations, but some of the equations are given in the book and used in the Lon Kappa problems. So again, you're going to have to read the section on antennas to do some of the Lon Kappa problems. An antenna is alternating current which generates electromagnetic waves. So we've been talking about waves. Where do they come from? Well, they're produced somehow. Radio waves are produced with alternating currents. So you have a big antenna, you have a big radio antenna here. There's some circuit which generates an alternating current. Alternating current produces electromagnetic waves. And for the kind of frequencies that can be produced, these would be radio waves. Now, antennas are used also to receive waves. So this would be a transmitter. This would be a transmitting antenna. The circuit creates current which generates waves. But you could also have a receiver. So this could be a receiver. A receiver receives the waves, and the electric field in those waves generates an alternating EMF around the receiving antenna. And then you connect that to a radio, some kind of circuit. You can collect the information that was generated by the transmitter. So that's how radio communication works. The communication is wireless, just goes through waves, through empty space. And to create and receive those waves, you have to have an antenna. It's just a conducting wire. So you'll need to read the section in Fisher about antennas for some of the line kappa problems.